三个 OK。
好。
罗盘到罗盘，对角。
Okay, let us start again. There's a good chance I need to leave a little bit earlier today. I want to start earlier. It's just a simple example that if I assume A is a matrix, hit 1, 1, 0, 1. Now its eigenvalue at 1. Its eigenvector eigenvalue 1, 1, 0, 1 times 1, 0 equal to 1, 1, 0. Right? So this one is your eigenvalue. This 1, 0 is your eigenvector. Alright, this is simplest example for eigenvalue and eigenvectors. So for you to understand what we mean eigenvalue, this eigenvalue, this eigenvector. In the side app, you can use a function's equivalent to EIG in the main app. So in the side app, inside app, there's a function called spectrum, SPEC, I think. So SPEC, if you give them A, and they give you two matrices, U and say V. And then if you do this, and this is the eigenvector matrix, this is the eigenvalue matrix, and this is the eigenvector matrix. I think maybe upside down, I don't know. I'll just make a guess. And this is the eigenvalue matrix. I know the eigenvalue matrix is diagonal matrix. And this is eigenvector matrix. You see it? Okay. So in the main app, you use EIG. In the side app, you use SPEC. That's the all small characters. Small characters. They automatically compute the eigenvector matrix for you, eigenvector matrix for you, and eigenvalue matrix for you. But eigenvalue matrix is diagonal matrix. That matrix gives you number 1, number 2, number n, and it's all 0, 0, 0, 0, 0, 0. 0, 0. I give you n by n matrix, n by n. If A matrix is n by n. All right. I use Scilab to compute eigenvalue, eigenvectors. I'm using to it. I used to it. So, and it's free. Okay. Any we can think again. We can switch back. All right. Then assume we don't have that problem. This is the definition of system bit stabilities, and so the normally to determine the system stability, we have to solve the eigenvalues and check eigenvalues to see if the real part of eigenvalue are negative. If all real part of eigenvalue are negative, means the system is stable. But in the second order system, you don't really have to solve eigenvalue of the system to determine the system stability. We can check this positive definiteness of the matrix M and zeta and K, then we'll know that the system is stable or not without solving the eigenvalue and eigenvectors of the system matrix. So the advantages of this is that you really don't have to solve eigenvalue to do it. Although to solve eigenvalue is very simple, it's easy. Just go to Scilab and call the SPEC, then you will get it. I'm not sure my spelling is correct, but you can go back and check. You can type help and then eigenvalue, and it will pop up the help menu for you. Okay, now I'm going to talk about the dynamics feedback. There's a dynamics feedback. Okay. I'm going to talk about dynamic displacement feedback and dynamic acceleration feedback. We know that direct, be careful, the direct displacement feedback won't dissipate energy. We know that. Direct acceleration feedback won't dissipate energies. Now, if you don't have the luxury of velocity measurement, assume I just don't have velocity measurement device, then what can you do? Nothing? No. You still have some other way to do it. That means you have to estimate the velocities. Now, in theory, you can differentiate the displacement measurement to get your velocity feedback. Agree? Or you can integrate the acceleration to get your velocities. That's true. I say that's in theory. But in practice, we don't do that because your measurement always got noises, got uncertainties. When you differentiate a signal with noises, with uncertainties, you amplify the uncertainties and also noises. So you don't want to, you can't trust that differentiation at all. In other words, you might gain more noise information than the system informations. That is no good. The same thing when you integrate accelerations. The problem is if your accelerations has some bias, when you integrate the bias, then you are growing. And that's not good either. So then what else we can do? So this is what we call dynamic displacement feedback, dynamic acceleration feedback. In other words, we are creating some kind of velocity measurement. Well, it's not measurement. we estimate some velocities. Let me put this way. All right, it's just equivalent. So that's what we plan to do. If you have a velocities, then you may not want to do this. It's just feedback, direct feedback of velocities to dissipate energy. That's much easier. But if you don't have velocities measurement, then you can't just have a direct feedback. Then you got to do something else. That's what I mean. That's why the dynamics displacement feedback or dynamics acceleration feedback. We develop this kind of feedback to at least to compensate the lack of velocity measurement. Put it this way, okay. All right. Then what we mean dynamic feedback? If this is a system, then we have the Kc here. We have a Wc here. But this is Kc and Wc. I will explain to you what we mean in Kc and Wc. All right. Assume we have a sensors. And this is a measurement device. And then I say, okay, I ask my computer, I say, computer, you need to do more work. You cannot just give me a gain and multiply that gain, multiply the measurement by a gain, and that's it. That's too simple job for you. I don't need you. You can say, computer, I need more, and you can do more. Okay. Then computer say, okay, then let me do this. But inside the computer, then I give them a differential equations called MC WC double dot plus ZRC WC dot plus KC WC, and this is the dynamics. I call it the virtual dynamics. It does not exist. It does not exist physically. It only exists inside the computer. Let me put it this way. Understand? I ask the computer to integrate that equation for me. And that MC, ZRC, KC are the design parameters. The designer, me, I can assign value, MC and ZRC and KC, to the computer. And I also make sure MC is positive, ZRC is positive, and KC is positive. Can I do that? And then my UC, that's UC. This is all virtual system. UC is a virtual system equal to KC parentheses W minus WC. So I'm saying WC is a virtual WC, but W is the measurement. It's come from here. It's from my measurement. So only the real value is W. All the others are just a virtual system existing in the computer only. All right. Then why I want to do that? All right. Let me show you. So I designed a command signal. That command signal is UC. That UC equal to wait a second. That UC equal to minus KC parentheses W minus WC. This WC is coming from the computer. The computer will integrate a differential equations to give me WC. And this W is from measurement. Okay? Then what do I gain if I do this way? What do I gain? Now, that's we call, so there's a dynamics involved here. It's not just a direct feedback. It's just not, I receive the measurement from the sensor and computer multiply the sensor measurement by a constant gain and then feedback. It's not simple job. It's more complicated. I want a computer to integrate for me. Like that, all right? So, again, the computer will create a WC, which is a virtual WC, and also that the system will have a real W, that's a measure, the measurement from W. And that's the one I want to do. All right. Okay, now what do I gain if I do that? Let me say, okay, now if this is the laser displacement sensor, and that is their specifications. If I do that, then what do I do? So this is the virtual system. That virtual system is, this is the system, and this is the virtual system, and this is the virtual system computed by the computer. That's only I call virtual system. So there's a virtual system like this in here, minus U equal to KC parentheses W minus WC. And then if this virtual system, this virtual system is the system that is embedded in the computer. It's not real. There's no real spring there. There's no real spring KC. There's no spring zeta C. All with sub C. C means computer, means control parameters. So C sub C means control parameter. Those are the gain you can design for it. If you do this way, computer will compute the WC and with W, and the computer will give the KC and the feedback to this system, and that system, computer doing the system, and that system is, this is the computer system I just give to you, and that equivalent to the passive system. If you think this is the passive system, and that computer will do exact the same as this passive system. Do you understand what I'm saying? No? Look at this. Assume there's a real system. Forget about this virtual system. Assume I have a real KC here. And this is my system. And this is I put another KC, another spring here. I put another MC here. I put a despot zeta C here. And this is my overall system. And then we can see that the system is stable. Agree? Has to be. Because we have a dissipation. We have this, we have what? We have this despot here. And that despot will dissipate energies. Agree? So there's no problem. If this is passive system, assume this is the whole thing is passive system. All right. What I want to do is, I want to replace the passive system, this part. Cut this off. Because I cut this off, I replace by what? I replace by this. I replace by this, by this, by that, by that. Can I do that? Then you understand better now, right? So the computer, based on the Y coming out, and their computer be using these dynamics equations. This is not direct feedback at all. So there's dynamics there. There's dynamics equation there. And that dynamic equation is a virtual. It's not real. But they act equivalently to the passive way. Does that make sense? They will give you exact the same force. If I do this way, and this force will be exact the same force as this force, as this force. This will produce a force like this. And this going through this KC. So another side of KC is minus U. So this piece I replace by an active feedback. This is passive, and I replace that active feedback, and That's what I'm talking about. All right. And this I call virtual system is the system that computer is computing. So that's the exact the same concept as direct feedback, except I put more work into the computer. This work has to integrate, the computer has to integrate the dynamic equations. Not just multiple the measurement by gain. Understand? Any questions?
The question I want to ask is the visual system, the mass matrix, the strictness matrix, how do you choose it?
Right. That's what we need to talk about that. Okay. This the gain, because you choose zeta c and choose keta c and choose keta c. If you choose more zeta c, means you get more damping, for example. If you choose kc and kc, the kc here, the kc there, you have to be, to choose this kc means to transfer energy from this real system into the computer system. For example, then this kc has to be chosen such that this virtual system oscillate with this system. Okay. So I'm just talking about a concept now here. I did not talk about how do we choose this delta C and Kc. And this delta C, Kc, MC, we call the control parameters we need to determine by some methods. So the step is here. As soon as the computer receives a real W measurement come in, then they start integrate this equation to get WC. All right. Assume we already give the MC, delta C, and Kc. Then they will integrate this equation to get WC. Then as soon as we get WC, we will be able to put here, we will be able to get W from the measurement minus WC computed from the computer, and then parentheses, then multiply by Kc and put a negative sign here, and that's the force I give to the system. Understand? So the trick is, computer has to compute WC with giving the measurement W. As soon as they got that, then they use this formulation to compute U, and that U will be the force. And that force will be the force provided by the actuator. Understand? Any questions? Computer integrate is easy, right? It's not difficult. It's you're talking about milliseconds. Integration by a computer is it's very, very easy. It's not difficult at all. All right, and that, well, I think I'm gonna stop today here because I don't have, I run out my time. I need to do something else quickly, and we have about 20 minutes left. And so, but I want you to go home and think about this. And if you have questions, you can come back to ask next week. And if you don't understand this, then I cannot continue. If I continue, then you'll get lost after this. So you got to understand this concept first. That we call dynamic feedback. All the control methods are dynamic feedback. From now on, you will learn all the control feedback, which is dynamic feedback. The optimal control is dynamic feedback. All others are dynamic feedback because if your system is 10-degree freedoms, then in general you really don't have all the state measurement. The state measurement include displacement state and also velocity state. If you want to have a direct feedback, you have to have all the state measurement, which is not the case at all. For example, this building, we may have a sensor, maybe one sensor at the top of the building, and another sensor maybe the second floor of the building, and maybe you can distribute, say, 100 sensors in this building. But this building may have 1,000 states. So for those states we don't have any measurement, then we have to use those states you can measure to estimate the state you don't measure. We call state estimator. We'll talk about that later. All right. So the trick here is this one here. The trick here is that because we don't have velocity measurement, how can I have a energy decay without velocity measurement? So we have to use this called virtual zeta C, which is not real. That's created by a computer. Computer create this virtual zeta C and give a virtual WC dot. Then we'll be able to prove that this kind of system, we know that if this is a passive system, it's a stable system. If this is a passive system, right? Now we just try to what we try to do is we try to we say, okay, now because we know the passively this is stable system. If this is a passive system, this is a stable system. But part of the passive system can be replaced by the computer and actuator and sensor. That's all. Okay? Understand? Because that we'll be able to add call WC dot. We'll be able to have the zeta C dot here there. So my computer will mimic the passive system. That's all. The job of computer is to mimic the passive system. Understand? Any questions?
老师，你刚刚说那个 WC 是用积分计出来的？
对 ，WC 是用积分
依
计
据谁？
Yes. If we have this input, we can integrate these equations. All right. Any differential equation you can be integrated if you give the initial condition WC and WC dot, and then you give them input. This is the input. You give the input to the differential equations. You give initial condition to the differential equation. Then you have what? You have particular solution. You have homogeneous solutions. If initially you say WC equal to 0, W dot equal to 0, then you don't have a homogeneous solution. You have only particular solutions. That depend on your input. Agree? Normally we assume WC equal to 0, W dot 0. So we forget about the homogeneous solution. we just use the steady state solution for this. Understand now? Right? Any differential equation is integrable by a computer if you give them the forcing functions. Agree? Right? He has done a lot of equations numerically. That's easy. That's not a difficult job in a computer. We'll explain this later, next week more, because this is really mimic to the TMD. All right. We just replace the TMD by the computer and by the sensor, by the actuator. That's all. The simple explanation is, how can I replace a passive TMD by an active feedback control? That's the job. That's what we call the active vibration observer. Yeah. AVA, active vibration absorber. All right, any questions?
剩下的 KC 还有那个 MC、WC 那些都是我们自己就KC 跟 MC 那个是直接是我们是电脑直接测出来设出来。
MC, Zeta C, and KC, we have a method to help you to determine them. We have some method, and that will help you to design a good MC, good Zeta C, and good KC. We'll talk about that later. Okay? It depends on your performance. It will be always stable, but it depends on your performance. For example, look at this passive system. This is MC, Zeta C, and KC. This system always stable, right? Agree? It cannot be unstable. This system, if this is a passive system, there's no way this system becomes unstable. Then how about the performance? Performance will depend on KC, Zeta C, and MC. So depending on your performance, if you know what kind of performance you want to be, then you can base on that performance index to design MC, KC, and Zeta C. Understand? Okay, 15 minutes left. We make up this 15 minutes, maybe some other week. Yeah. All right. Any problem or any complaint or anything else? If no, then we end it today. This week, and then we see you next week.
我们说这个大于是指里面的 element 很大。